Hi everyone, my name is Tovio Roberts, and we're going to have another Galvanize study hall. If you are in the Slack, then you can ask me questions from the materials. Otherwise, I am going to be working, just starting where we left off last time and going through our materials on basic prep. So we finished up intermediate Python last time. We looked at dictionary accumulators. Those are going to keep coming back. We're never going to stop looking at dictionary accumulators, just because, in part because they're throughout the materials, right? And they're very relevant to the technical interview. For the moment, or for the next little bit, we're going to be looking at some basic stats. And I'm probably just going to cover this unit for today. Central tendency, 5-number summary, and variance and standard deviation. And then next time we'll move forward. So probably I'll just cover these and write relevant code for all of it. And, talk lightly about it. And then probably do more dictionary accumulators, actually, since so many people are at the moment preparing for the technical interview. So, yeah, I don't see any questions yet. Let me just take another look in here. Yeah, and this is my environment as usual. I've got VS Code here. I've got a terminal here. I might resize this a little bit and get a little more real estate over here. Yeah, something like that. And yeah, and we'll just, kind of take a look at our basic summary stats. So when we say, when we're talking about statistics in terms of machine learning, a lot of the time we are talking about some higher level concepts that are not going to be in your, say, Stats 101 kind of textbook. Speaking of which, if you are interested in stats textbooks, there is, if you're, let's see, OpenStax has a series of textbooks that are really good if you like that more, basic textbook approach. So we've got, let's see, I should just go to openstax.org. So these books, if you're not familiar with them, are pretty good textbooks, and they're openly developed by teams of experts. And, we can just look at, let's look at all the math that's here. So, pre-algebra, pre-calc, calc, trig, and then there's a couple levels of statistics. We've got, you know what? They used to have calculus-based statistics here, but it doesn't look like they do now. Could have sworn. Either way, let's just take a look at this. Yeah, this is all your basic statistics. This, if you're looking for problems to work, especially, things related to, say, Poisson or binomial or geometric, there are problems, right? There are example problems. There are, there are, oh my gosh, thank you for the pop-up. These are just good materials. So openstax.org, if you're interested, they are pretty cool. I've definitely tutored people out of these books at different times, and I think they're good. They can be a little terse at times, but, that's... anyway, when we're talking about statistics and machine learning, we're kind of working from this premise that machine learning comes out of this idea of statistical learning. And, what we're kind of working toward in our materials is the requisite foundational knowledge for, in our materials, we're working at the requisite foundational knowledge to be able to look at a book like this book, Introduction to Statistical Learning, which we do reference in the DSI. We also recommend that people, we recommend people try to work through this book. It's a really well-written book, gives a great foundation for machine learning. They call it statistical learning, but we plug this book all the time, and it's free. It's openly available online. If you go to our YouTube channel, see if I'm, yep. And you go to look at our playlists for our channel. Let me see if I can just go to our channel. I actually just put together a playlist here of the ISLR. Oh, let me close that video. Oh gosh, where is it? Functions, sets, solutions. Oh my gosh.
All right, we're starting to work through some.
Sorry, I keep clicking on videos on accident. Let me just do this. I'm gonna grab this ISLR playlist that I put together a while back. Basically, these are all the videos that are linked from this landing page for the ISLR. Slides and videos are available separately here. I just put them all together into a playlist because I find that to be modern, I guess, instead of having them all embedded in a video. So I just put those in our Slack thread. Yeah, they're good. They're fairly short. They're usually not longer than, say, 10 minutes. They walk through a concept that's in the book, and they cover the entirety of the book. And there's a whole bunch of like dad jokes thrown in there just for good measure. So, when we're talking statistics, we might be talking central tendency, mean, median, mode. We might be talking set theory. We might be talking distributions. And maybe I'll just pop out here and we can look at everything that we cover. We talk basic and conditional probability and discrete and continuous probability distributions. This set of materials is sort of what is prerequisite for the materials that you need to know for the DSI, if that makes sense. So, let's say you cover all of this, you pass your technical interview, and then you're opened up into the pre-course. The pre-course is going to have more materials related to, linear algebra a little bit. We're going to have some linear algebra materials. We're going to have some more advanced probability and statistics materials. We're going to have some concepts that are in this book. Things like if you look at chapter 6, we've got, is it chapter 6? It's chapter 5, actually. So chapter 5, 5.1, cross-validation. This is something that going into the DSI, you want to have some kind of understanding of, right? If you're in the premium prep class, we're going to talk about cross-validation tomorrow. You don't need to know this for the technical interview, obviously. You do need to know it for the start of the DSI, because you're going to be using cross-validation kind of the entire time. Cool. So this is a great book. That's the short of it. And, this is kind of the premise that we're trying to build you up to the ability to be able to read this book and effectively understand it. This and other sort of intro level machine learning books. Notice that this says with applications in R. So if you were doing R, you could code out the solutions and different problems in this book in R. But let me just show you something. I'm going to just look ISLR, and I'm going to say Python and say GitHub. And notice this brings up a bunch of different people's repositories who these people have all gone through the ISLR and are doing it in Python. So they've translated all the problems into Python, right? Here's chapters 3 through 8 that somebody has done. I think I could look at any of these and they're going to be chapterized, right? 3, 4, 5, 6, 7, 8 through 10. And I think all of these are going to start at 3 because There isn't really any coding before chapter 3, if I remember right. But, so because it's in R, don't let that put you off. If you're interested in reading this, again, if you've already passed the technical interview, then it's time to start looking into this book and into other materials to shore up your quantitative and coding knowledge. If you are still yet if you have not yet passed the technical interview, then I would say wait on this until you pass the technical interview, unless you're aiming for the DSI that's going to start in January. If you're aiming for October, I would wait, get past your technical interview, keep doing code wars, keep doing practice problems, get your Python really up there, and make sure you pass your technical interview. And then I would say move in the direction of building out your foundational knowledge in machine learning. Let's see. Now, I think I did throw this book into the Slack. Yeah, I did. Okay. So we're looking at, basic summary statistics. Oh, there's a question in the Slack. If we have time, can I go over integrals in PDFs? I have no idea how to go forward with challenge number 3 at PDF. Let me just take a quick look at that one, and I might put you off by a day if that's okay, just so that we tackle this in one go when we get there. You're looking at challenge 3. But they're in very. Okay. Yeah, do we walk you through integration here? Oh, we do. Okay. Yeah, this is the kind of thing where I'm going to need to have my document camera in front of us, and I'm going to do it by hand, if that's helpful. And with some of these, well, definitely with this, we're going to put some solutions videos in here before very long. That one definitely deserves a solutions video, and those are still in production. So, if you could could you direct message me on that one, and I'll put that in my queue, because I might be able to just get my document camera set up tomorrow and put a solutions video in there for that one specifically, because it is a harder problem, and yeah, I could see a lot of people benefiting from that. So, oh, and just a heads up, you don't need to be able to perform an integral on a PDF for the technical interview, just so you know that. But it's definitely something that it's fun when if you learn how to do it, it's pretty fun. And yeah, integrals can be easy depending on how you approach them. So I'll try to get a couple of videos knocked out tomorrow for this, and I'll embed them in the Learn materials. And then when we get to them in the study hall, I'll have a document camera with me so that we can work through things by hand. Okay, so we're talking summary statistics. And when we say summary statistics, we mean mean, median, mode, measurements of central tendency generally. And we're talking 5-number summary, variance, standard deviation. We might actually talk about error metrics as well, although those relate very directly to all of these. And you don't need to know these in depth for the technical interview. It's more that you want to know that they exist, and you're going to learn them in the pre-course either way. So let's just start looking at the mean. So mean is pretty straightforward, and it's a concept that we're all already pretty familiar with. So we've got the arithmetic mean, and all this means, and I'm going to try to do this for our mathematical formulations in general. So let's say we have a list of values, right? And maybe I'll just we've got 1, we've got 3, that should be a 3. Let's pretend that's a 3. 4, 5, and 9, let's say. So in Python, we start this indexing at 0, right? 1 is the 0th index, is at the 0th index. 3 is at the first index, at index 1. 4 is at index 2, etc., right? And our indices go from 0 to 4. In our mathematical formulations, that's not true. Generally, we're going to start our counting at 1, right? So if we're thinking about this, we're going to start at 1. And so in this case, let's just break these symbols down. This is sigma, and this is, or it's capital sigma, and this is our summation, right? When we see this, we think we're going to sum whatever's over here, right? Whatever's here. And what we're summing here is A, is all the elements of A. Well, let's not pretend, let's just say that A is this list, right? A is this list. So 1, 3, 4, 5, 9. I is the index of the list, except remember in the mathematical formulation, we're starting our indexing at 1, not 0, whereas with Python, we're starting at 0. If you're coming from a language like R or MATLAB, indexing does start at 1 to be, which follows the mathematical convention. In general, in computer science, pretty much across the board, we use 0-based indexing. It just makes way more sense. Anyway, so this is the first element, and notice we're not doing anything to it. We're just saying, okay, well, there's going to be 1, and then we say, well, it's going to be plus the second element, which is 3, plus the third element, which is 4, fourth element, which is 5, plus the fifth element, which is 9. Notice we go from, this is our from down here, right? This is from I equals 1 all the way up to n, I equals n. So n is just the length of this list of numbers. So I equals 1 all the way to the end of our list. And what we're doing is summing all of them. So a sub 1 is 1, a sub 2 is 3, a sub 3 is 4, etc. in the mathematical formulation. So we're just adding all these together, and then we're multiplying it by 1 over 5. Or you can imagine we're taking that summation and we're dividing it by 5. Now, this is the average we all know. Oh, shoot, I wish I would have remembered those numbers. What was it? It was 1, 2, 3, 5, 9, maybe? And we said that this was A. Oop. Let me zoom that in. So 1, 2, 3, 5, 9. So if we want to write a function that performs the arithmetic mean, all we really have to do is add all these numbers up and divide by the length of the list. Now there's a couple ways we can do that. And I'm going to just write a function called mean, and it's going to take in a list of numbers. I could just say this is the sum of the list divided by the length of the list. And then we're going to just return that, right? So this is just the mean of A. 1, 3, 4, 5, 9? Okay. 1, 3, 4, 5, 9 is what it was. Thank you. So if we're considering what is the central tendency of this, well, we can consider the mean as one measurement of central tendency, right? So what does this get us? Let's do python delme.py 4.4. Okay, so this has a mean of 4.4, and when we look at this, that kind of makes sense, right? If we were to kind of spread this out along a number line, we can get that impression, and maybe if we're considering where this lies, it does kind of look like it's right here. Like our central tendency does sort of seem to be right there. Now we could weight this we could put a whole bunch more ones in here, and we could see how this changes. And you know, you can imagine that there's more weight in this number line over here on the 1. So, you know, this is all pretty intuitive, I think. This is going to drag our central tendency to the left. We have a whole bunch more of these 1s, and we're dividing by a larger number. So we're adding less than we're dividing. And, you know, that just gets us a value that's going to be lower. So let's keep in mind this, this just A is 1, 3, 4, 5, 9. And we'll just leave it at that. Let's see if there's anything else in this lesson. Oh, yeah, I just want to show you another way you could write this if you wanted to use an accumulator pattern, which is less efficient, but, you know, you can use, this is just to sort of drive home that point. You can pretty much always use an accumulator to solve something. If we want to do that, let's make something, I'll just call it accumulator. Set it to 0, and I'll say for num in list, the accumulator is going to be incremented by the num, and then we're just going to return the accumulator divided by the length of the list. This will do the exact same thing. There's no, you know, logically it's doing it differently, but it gets us to the same place, same exact number. In general, this is how you want to do this, because these built-in functions will be faster, and they'll be a little bit better, less code, a little bit cleaner. Okay. So we start off telling you about populations versus samples pretty quickly here. And in statistics, this is really important. And it's something that it's a type of knowledge that you take for granted quite a bit in machine learning data science. Well, what is the difference between a population and a sample? I like to put this in terms of, often in terms of stars, right? There are a lot of stars in our universe. If we knew the weight, or let's say we knew the mass of every star in the universe, then we could give the mean of all the stars in the universe, right? We could give a what's called a parameter. We could give a population parameter for that would represent the average mass of all the stars in the universe. We can't get that information though, right? We can't even view all the stars in the universe. We can't even view a large fraction of them, right? But let's say we can, let's say we can estimate some sample of all the stars in the universe, and we make the assumption that that sample, that subset of the stars, we say that that is representative of all the stars in the universe. So we're making an assumption there, right? We're deciding that we know a little something, we know enough to know that this is a good representation of all the stars in the universe, right? So we take that and we perform this operation. We get the mean of that. We're going to say, well, this is a representation of the average mass of all the stars. But we need to assume that we're a little bit wrong, right? We need to assume that we're a little bit incorrect here. And when it comes down to it, a lot of the time in statistics and machine learning, we are trying to quantify our uncertainty. And in this case, we're not really talking about uncertainty. We don't get too much into uncertainty in these materials, but consider that we don't know. We don't know how accurate our average of the star's masses is, right? And we have something that we think is representative, but there's a chance that we're way off, right? Like, what if there's this huge cluster of stars with incredible mass that are outside of our perception, our ability to perceive, given the tools of measurement, the tools of observation that we have. Well, we might be very far off in our idea of the average mass of stars in the universe. So, we do our best to deal with uncertainty, but we're almost always dealing with a sample, right? And so we have to quantify our uncertainty as best we can. And when we're talking about measurements from samples, we call those statistics, right? So if we have a sample of the stars in the universe, if we are saying, well, we think that this is the mass, the average mass of stars in the universe, that's a statistic, right? It would be a parameter if we knew the actual mass of all stars in the universe. Okay, so that's kind of just a statement about population versus sample. This doesn't really affect our mean. It can affect the way we write our mean, like how we represent it in mathematical formulation, which we don't say here. I do believe we say it in a following lesson. More often. Oh no, we say it right here. Let me just blow this up. Perfect. Okay. So, if we're talking the population mean, the mean of all the stars in the universe, then we use this Greek letter mu, right? Which is sort of like a U with a tail in the front. That's mu. And often we'll also kind of use these for samples too, as it turns out. But, so when you're reading through code on sklearn or some other machine learning library, you'll see this word used to represent the mean. We'll often call it mu, okay? Whereas in general, what we would call the mean for a sample is x bar. And that's just, right, this is just an x with a bar over it. When you see it written, in code especially, you'll probably see x underscore bar, right? Because we can't actually do an overbar on an x. So this is just a difference in our naming, right? These are semantics. When you say mu, conventionally you are referring to a population mean, right? If you say x bar, conventionally you're referring to a sample mean. The capitalized x bar is also used, but honestly, I never use that because, well, for exactly this reason. Capital X is often used for a random variable, and I just think it's sort of a collision in naming conventions. One thing you'll see in statistics and linear algebra and differential equations and if you get into Fourier, like math related to Fourier transforms, everybody uses different symbols, and it's a little bit frustrating. You kind of have to learn the symbols as you go. We try to be pretty consistent here, but just a heads up. Okay, so that's all I have to say about mean. Let's talk median a little bit. Median is sort of offhand it seems like a very simple way to determine central tendency, okay? It's just the middle value. So when we're looking at A, we're just saying, okay, well, the middle value is 4. The median here is 4. So how would we figure this out? Programmatically, I might just say def median, and we put in a list. Well, we can return the length of the list, divide the index. Well, let me just do this. Let's say the median index, right? Because we're going to need the index of that value. That's going to be the length of the list divided by 2. And since it's an index, we need to make it a whole number. So I'll cast it to an int. And we'll just return the sorted version of the list. So offhand, we have this sorted, right? And I'll just go ahead and return. I'll do sorted of list, and then let's return the median index. So conveniently this list is sorted right now, but let's try this with an unsorted list and kind of just demonstrate what's going on here. So I'll just print this. Oh, name list is not defined. Of course it's not. Okay, 4, right? That's what we expect. We expect to get 4 back. So what happens if I'm just gonna go ahead and mash some numbers, and let's get the median of this. Notice I've got a bunch of different numbers in here. Some of them are very high, some of them are very low in comparison to each other. And our median is 7. Now, let's go ahead and print the sorted version of A. And we'll see both of these, right? So if we're looking at this, is 7 actually a good measure of central tendency here? I kind of don't think so, right? Like, this is kind of a strange thing. 1, 2, 3, 4, 5, 6, 7, 8, 9. This is our middle value here, but we want to be careful because this is kind of not very central, right? This is sort of, it's almost like we have two sets of numbers here. We've got these higher numbers and these lower numbers, and maybe these shouldn't belong together. This is the median, but it's not a very good measurement of central tendency. Now, if we're considering this to be one set of numbers, then let's also look at the mean of A and kind of see what that is. And let's take another look at this. Right? So 36 is somewhere, in here, right? 36 is going to be somewhere in here. And that does seem a little better here. So when we're considering mean and median, we often need to make a decision. Is one better than the other? Are they fairly equivalent? And in this case, I would say mean is much better than the median. So let's consider another set of numbers. Let's do this. All right, so this is 10 values, right? And given that this is 10 values, let's see what our median comes up with. So the median here is 5. Notice, though, that there are 5 numbers on the right and that there are 5 numbers on the left. So the median here should not be 5. And let's look at what the mean is. The mean is 4.5. 4.5 would be better. Is more accurate. But this is actually a problem with our median function in its current form. If we have an odd number of items in a list, then it's easy. We can just pick the middle value. But if we have an even number of items, then we actually need to take these two middle items and we have to divide that by 2. So we sum these two. 4 plus 5 is going to be 9. We divide it by 2. Our median in this case should actually also be 4.5, the equivalent to the mean. So let's do something about this. Let's say if the length of the list modulo 2, if this is equal to 1, meaning if it is odd, then we're going to perform this operation. Otherwise, we're going to grab the two middle values, right? So how do we do that? I'm going to do this in a little bit of a verbose way, but it'll, just to try to show you what's going on here. Notice up here, our median index in the original form got us 5, right? Which is our upper middle value. So I'm just going to grab this, and I'm going to say this is our upper mid. And then our lower middle value is going to be that same thing minus 1. And then we can just return upper mid plus lower mid divided by 2, right? Oh, sorry, that's our index. So we're going to have to grab those indices instead. So we'll just get from list, we'll get list sub upper mid plus list sub lower mid. And then we can divide that by 2. And then, oh, that's it, isn't it? Let's see if that worked. Yeah, that gives us 4.5. So now our median function can accommodate both even length and odd length lists. Now, if I wanted to make this more dense, maybe I could make a one-line solution. I'll just go ahead and do that. I can just take this upper mid and I'll just put it in here. And I'll take the lower mid. Oh, whoops. What did I do? I did that wrong. I actually want to replace that. And then our lower mid. And this is going to get this onto one line. And I'm not saying that's preferable. I'm just saying we can do that. And I can do the same thing up here, right? I can take this median index and just throw it in there. And that'll get us onto one line there as well. So, you know, it's your call whether or not this is cleaner than the other version. One might be a little more explanatory than the other, but if you know what's going on here, it's pretty straightforward, right? So, so there are going to be times where you want to use median over mean or mean over median. Notice in this instance where we have a range of numbers from 0 through 9, the mean and the median are the same. And so we have a very clear idea of central tendency, and we have a clear idea of how these numbers are spread out, right? They're all spread out in a certain way on either side of 4.5. And that seems pretty straightforward in there. So how do we represent the median? Well, let's see if we talk about how we do that in here. Notations. That's exactly what I'm looking for. All right. So these are two notations that we might use. I tend to use this one, although I do tend to say median, like the full word, just median of whatever it is. X tilde is less common. I pretty much have never used this. I almost never see it, but it's good to know that this exists, right? This is out there. Often, you know, you're going to, this is nice because it looks like a function, right? It looks like a Python function. So, you know, you could use either. Okay, we just covered median. And do we talk here about which one you should use? I don't think we do. Nope, good. So we'll come back around to that. Yeah, I guess we don't talk about it at all in here, do we? Well, we'll think about it a little bit more. Actually, let me just give you some data where we're going to consider the mean versus the median. And let's say we have the weight of fish in a pond, and let's say we've got fish weights, and I don't know. I grew up fishing. I don't know. Grew up in the country fishing, and there are some very light fish, and then there's some heavier fish. I don't know. So panfish in general are pretty light, and I'm just going to say, well, maybe we catch a bunch of panfish, and there's like one that's 0.5 pounds, I guess, and one that's like 0.65 pounds, and one that's 0.49 pounds, and one that's let's say 1.2 pounds, right? Like a relatively big one. And then let's say we were catching some panfish, and we ended up catching a bunch of like heavier fish, and maybe there's one that's 4.5 pounds and another one that's 5.6 pounds and one that's 5.5 and one that's 6.4 and one that's 3.9 and one that's 5.5, and let's say that was our fishing trip, right? Okay, so one thing we might want to do when we're first considering this is just printing the sorted version of the fish weights, right? And this might give us some insight into how to think about the central tendency of this. So here we've got our weights of these fish. And if we're thinking about central tendency, it kind of seems like we've got a lot more weight in this higher range of values. And, the first thing you might consider here, and this is a good thing to consider, you might consider that this is actually two data sets, right? We've got our panfish, and then we've got our bass or pike or whatever we're catching over here. And those are potentially things that we should keep separate. But let's say we're not keeping it separate. Let's say we're just asking, well, what is the central tendency of this data, right? Of all this fish data? What on average is our expectation of the weight of a fish? Again, that's a bit of a flawed question because it kind of seems like we have two different distributions here. But let's go ahead and look at the mean for our fish weights. And let's also look at the median. So if we look at this data again, and let's just do what we did before and just pull this up, we might want to ask the question, which is better, the mean or the median? And the first thing we're printing here is the mean, which is somewhere around 3.379, right? So our mean is somewhere here, right? So, 3.4 roughly, right? Somewhere in here. That's our X bar. And our median is up here, right? So we've got, our median, which is somewhere around, it's roughly 5, right? So which one of these seems better, in terms of our expectation of, the weight of a fish we might catch? This is an arguable point. We have a sort of pure expectation, which is our mean over here, right? This is kind of a pure expectation because it is the average, the arithmetic average. But I would err on the side of the median here. And that might be a hard sell, but we are getting more of these larger fish, right? And I think median here is probably giving us a better indication of, of what we might be seeing, what we might expect to catch. So you have to put some critical thought into it. Statistics are like that in general. You have to pare down what you're trying to figure out. So a question came in, and let me see. This is a question from the Python materials. Let me pull those up. In general, when you ask a question, if you could also put the URL to the question, that would be really helpful. That way I can just open it up. So this is Unpacking a List Challenge, number 3. And I believe that's under List Basics. Let's see. No. List slicing, list membership, accessing list values. Maybe it's under accessing list values. No? Okay. One sec. Oh, great, thanks. Somebody just posted in the URL. So we'll just go down to that. All right. So we've got a list here. And I'm going to go ahead and look at this. So unpack the list below. This list needs unpacking. Each of those are strings in the list. The first element should be stored in the variable we. The second element should be stored in the variable r. Unpacking in our list. So list unpacking is pretty straightforward. You know, we're going to say we are unpacking our list, and that's going to get the list. So what's going to happen here? Oops. Oh my gosh, VS Code, you're so helpful. Oh, thank you. You know, I don't need to start in on complaining about VS Code today. Okay. So what's going to happen here is this is going to get put into we. List is going to get put into R, right? Needs into unpacking, and unpacking into our list. So that's really all that's going to happen. Notice that, you know, all we're doing is accessing all these values and pulling them out and assigning them to the individual variables. One of the things about this, we definitely need to have as many variables as there are items in the list. Otherwise, this won't work. So, you know, each of these items will just go into its relative variable in order. And, you know, this, I should just be able to paste this back into here, and let's see if it works. I'm assuming it will, and it did. And in fact, the explanation code here is exactly what I had typed up above. Cool. Hope that helps. Let me take a look at. Oh, interesting. Interesting. Okay, let me show you your code, and because I think you are not thinking about this incorrectly. Let me say that. So I'm just going to reproduce your code here. So this is list sub 0, right? This should be list sub 1, sub 2, and sub 3. Oops. Should probably put those in there. All right. So this is unpacking a list, but it's doing it very manually. And let's just see if this works in here. So this should also work. And I wonder if because you're also printing. You are printing we are unpacking our list. Let's see if that doesn't work. Okay, yeah, so that should have worked as well. I'm not sure why your code isn't running, but your code should also work unless I'm not seeing an error that's in there. I couldn't copy paste it directly, but your code looks exactly the same as mine up here. So that should work also. And you know, this is a good point. It's kind of a good point that you're bringing up about list unpacking. This approach to unpacking a list is completely valid. You know, what you're doing here is the direct equivalent to what I'm doing here. You know, these aren't really different. You know, I think this single line solution is nicer, but what happens if you have a list where the length changes, right? Where it's a longer list or a shorter list? then this line 5 wouldn't work anymore. Whereas your lines here would always work, but it really just depends on the problem you're solving. And you really start getting into list unpacking when you get into tuples and function returns anyway, which unpack in the exact same way. Huh, yeah, it returned an error. If it returned an error, I'm not entirely sure why. It's possible that there had been an update made and maybe there was something wrong with this challenge. Try hard refreshing the screen, which is, if you're on a Mac, it's Command-Shift-R. Let's take a look. Oh, I see. Okay, I'm just gonna screen capture this to show it. So the error that we're seeing here is an unexpected indent error. This is something in Python. All that really means is that there's in some way there's some extra white space that's happening. And let me look again at your original code, because maybe there's something in there that I didn't see. Oh, I see it now. Okay, let me point this out. What's happening? Okay, so this does make sense. Why you're getting this error, and I'll just try to get your code up and visible. So notice the alignment here. List is all the way to the left. I think the edge of the screen is here, and notice that this L. Notice that you're indented by a space here. So that's what's happening there. All of this needs to get pulled back just a little bit. It just needs to get pulled back one space. That's why you're getting that error. Does that make sense? And yeah, so whenever you see that unexpected indent, that's absolutely what's happening there. It's just that you have an extra white space, or you've got a tab where you don't need a tab. That kind of error comes up quite a lot. Actually, it comes up for me a lot because Python is it's fairly strict about that. Okay, so let's go back over here. We just talked mean and median. So let's talk mode a little bit. Mode is a bit different, and we're going to think about it a little bit differently from mean and median. Now, what happens if you have a data set that is, has qualitative, not quantitative information, right? Like categorical information. Let's make something called cats, and I was just tempted to write down cat names from the Cats musical, and I'm like, those are really long. Also, I hope some of you saw the Cats musical movie. Wow, that's all I can say. Wow. Okay. Okay, so instead of that, I'm just going to come up with some other names. Let's just Fluffly. Okay, that's good. Oh gosh, on the fly. Fur. Let's call this cat. Let's say a few people name their cat Fur for whatever reason. I had a cat named Pierogi. Mittens. That's a common cat name. Mittens. Let's do Whiskers. And Jaws. How about that? Okay. So these are all potential cat names from some sample of cat names. And how do we get some idea of central tendency here? It turns out that's like the way that we do that, a way that we do that is we ask what is most common. And we can't get a clear expectation here of of what we're going to see out in the world. But you can think about it like this: like if you are in Denver, how about this? If you're in Denver and you ask a random person on the street what extracurricular activities they're into, you can kind of take a guess, right, as to what they're into. Skateboarding, snowboarding, skiing, hiking, right? Yoga, and not to stereotype people in Denver, but it's something. It's something for real. And how could we approach this as in an analytic, kind of critical and statistical way? Well, we could take a large sample of the population and ask them, survey them of what they're into, and we could essentially take the most common things that people are into, and we could make a statement of, well, we have somewhat of an expectation that if we ask a random person, they're going to be into this thing or into this thing and that thing. And that's really the purpose of the mode, right? So how do we write a mode function? Well, we kind of just look for the most occurring item. So I'm going to write mode. So def mode and def mode on a list. I'm going to make an initial assumption, and somebody just said the Cats theater experience equals. It's not even a frowny face; it's a sort of like appalled frowny face. Yeah, yep. I literally went to see Cats because I read a review that called it an abomination, and yeah, I was like, I should go see that, and I've never left early in a movie, and then we left before it was over. I felt weird. Let me just say that I felt weird. Sorry if there are any people who love this movie. I sort of love it. In a very complicated way. I'm glad it exists. Okay, so let's say most occurring is going to get the initial value in our list. So you can imagine we're going to look at fluffly first, and from there we're going to check each subsequent item in the list. So I'm going to say for item in every other item in the list, and I'm going to use this kind of notation where we start at the second item, which is index 1. We start at fur, and we're going to say we're going to do this in a very kind of in a very simple way. Since we've got a single list, we can just count each item, and if the count of that item is greater than the count of the currently assumed most occurring item, then we just update most occurring. And this is just some simple logic that's going to get us to a result, right? So we'll just say most occurring is going to get the item, and then we can just return the most occurring. So what we should expect to see here, let's say print mode of cats, and of course we get fur because, well, it's the most occurring, right? So what if we have another cat named Mittens in here? Our function is only going to accommodate one mode, right? So we've got a primary mode, and then we've got another primary mode. This is actually, we could call this bimodal, right? There are two modes, let's say. It's not the best use of the word bimodal, even though there are two modes. There are other ways that we use bimodal, like if we have two normal distributions or say binomial distributions that are centered around different numbers, then we would say that those are bimodal with some sort of double peak and two modes. But we can use bimodal here as well. Now, if we wanted to adjust this so it returned bimodal, something bimodal, we'd have to put some extra logic in here. And let me just see if I can just intuit that really quick. So if the list of the count of the item is greater than the list of the count of the most occurring, then let's make this a list instead. Oh, should we do that? The thing is, we might have to. Well, no. I think this is easy enough. So let's do. Let's call something second mode, and let's put in here also list sub 0. I'm going to do this in a really kind of straightforward way. We could write better, more complex logic that would get us something a little nicer. But if the list of the count, if the count of the item is greater than the count of the most occurring item, then we're going to say most occurring gets item, right? And then let's put another piece of logic in here. If the list of the count of the item is equal to the list of the count of the most occurring, then let's say, let's put a second qualification in here, and let's say if the item is not equal to most occurring, yeah, I think this will work. Then our second mode is going to get the item. So let's try that, and let's say if most occurring is not equal to second mode, then let's return most occurring and second mode. And yeah, let's just return both of them. Like, well, it's kind of weird to return two things like that. So let's put this in a list, and else let's just return within a list, a length 1 list, most occurring. So let's try that. I think that should work. Yeah, oh no. That does not work. If most occurring not equal to second mode, of course that's not going to work. Hold on. All right, so we want to get mittens and fur in here. All right, so if list.count of item is greater than list.count of most occurring gets the item. And if list.count of item equals the list.count of the most occurring, let's just set this to none. So in this case, let's say if second mode is not equal to none. Let's try that. Okay, so now we're just getting fur. Okay. Interesting, because maybe somebody can see the error in my logic here, because mittens, the count of mittens should be, let's try this. Oh, that won't work because, Okay. There are 3 mittens here. List.count of the item equals list.count of most occurring. If item does not equal most occurring, then second item gets item. Second mode gets item. I've gotten myself into a little quagmire here. Anyway, let's just back this up to a single mode. There's a much better way to get something multimodal, and that's through arranging these from the most occurring to the least occurring. In fact, why don't we just do that? So let me do mittens, mittens, and mittens, and instead of this approach, let's do a completely different approach. Let's just make a dictionary. And I'm going to say for item in list, d sub item is going to get list.count of the item. Okay. And then we can return, oh, I think I have to, let's do this in the other way. Let's say occurs here. So this is our count, I'll just call it item count. And we'll say if item count is not in the dictionary, let's do it like this. Then we're going to start that, and then we'll say d sub item count dot append, and we'll append the item, okay? And then let's return I wonder if we can just return the max from this. So let's get the max. Let's do it like this, just to be sure. Let's get the max is going to get the max from d dot keys, okay? And then we can just return d sub max. So let's see what that does for us. Oh, name casts is not defined. Mode of casts. Mode of cats. Makes more sense. So we're getting fur. Let's instead make this a set. It would make a little more sense as a set, in fact. And let's change this to add. Oh. There was an error in my list. I bet my function worked before and I didn't notice because I had an error in my list up here. Great. There's something wrong with the data. Okay, dict object has now attribute add. That's because this should be set, the set constructor. Okay, mittens and fur. So that was a very roundabout way to get get all the modes from a distribution. But it worked, right? So we get both mittens and fur. I think my earlier logic would have worked had I noticed that I was missing a comma right there, because that would have made mittens the other mode. So we should be able to even make all of these multimodal. So what if we have 3 modes, right? This should work for that. So this is a much more portable function as opposed to what I was writing, which could only return 2 modes. This can return all your modes, right? We just get the maximum in the counts and we return that. Anyway, mode. That's kind of a long way around mode. Now, how do we represent mode? The main way that I represent mode is this first instance where, right, we just take the word, sort of like median, and we don't have this explicit letter that we use for mode in most cases. We do have this. I never see this again, sort of like the x tilde that we saw for median. With median and mode, we often represent them like this. And I think part of that is because we don't necessarily use them as much. We don't use them as much. I'll just say that. It depends on what kind of data you're working with and everything. But yeah. So, oh, interesting. So the example of mode here, the mode code snippet here, actually does use a dictionary and uses a similar approach to this. This looks a little bit more involved because they use the actual item as the dictionary key, whereas I'm using the count as the dictionary key. This ends up with a little bit less code. I kind of like it more because then I don't have to process this in the same way. Like ultimately, this has to process out these modes. Okay. Okay, and this other version of code uses counter from collections, which is fine. Oh, and then we've got a SciPy stats implementation. So let me just use this really quick and let's see what we get. So let's print, oops. Yeah, there we go. So we're gonna run the mode on cats and we'll just print that, see what we get. And I guess, so notice that took forever. And this is a thing about SciPy stats, which you should all learn how to use after you pass the technical interview. Notice that we're only getting a single mode out of this. We would have to specify a second mode or a third mode as well if we want to use it in that way. Okay. Anyway, we talked a lot about mode here. The short explanation is you have some non-quantitative data, let's say, or maybe it's quantitative, but it can be categorical, and you are wondering what you would expect to see if you choose from random, from the population, and we're assuming that that's going to be the most common item. Okay, so we've kind of talked central tendency already, but this goes into it a little bit more. So central tendency, is essentially a categorical description for mean, median, or mode of data sets. And these can be three different stats that can give you three unique insights, right? Like, let's say you have an online store and you sell a lot of a specific cactus that sells for $2. And then you've got all these other plants too, and some are $50 and some are $30 and some are $15. And, if you look at the mean, maybe what you see is that the mean cost of things that you sell is $16.40, right? And you look at the median, and maybe that median is a little bit higher than that. The median would probably be a little bit lower than that if you're selling a lot of $4 cactuses, cacti. But the mode is going to tell you that you sell a lot of this cactus, right? That you sell it a lot. And that is going to give you different information than what your mean and your median are going to give you. And likewise, mean and median are going to give you slightly different information as well. So it's all about, so much of this is about storytelling. You're talking about your data in some way. And mode can be this great indicator of the quantity of some occurrence, whereas median is going to give you a sort of a middle value that is resistant to extremes in either direction, and I'll demonstrate that in a second. And mean is going to give you sort of this pure arithmetic average. So the classic example of this, in fact, before even looking, I'm going to assume that this is an example that we have in here. Let's say we're talking house prices. Let's say we're talking incomes. And we have this sample of incomes from a collection of people. And let's say one person makes $24,000 a year. Let's say one person makes $56,000 a year. Oops. Let's say another person makes 87. Another person makes I don't know. I'm probably just going to do these in order so I don't have to sort them later. Let's say, 92. Let's say another person makes 105. And let's say somebody makes 463. Okay. So if we're looking at this, well, let's... Oh, I erased my mean function. I'll just copy this and I'll grab it from the prior lesson. And so we'll just have it from that. I'm going to grab my mean and a median function really quick. Okay. Okay, there we go. So, and I'll pull this down here. So I'm going to print the mean of this, and actually I'll print the incomes, and I'll print the mean of the incomes, and I'll print the median of the incomes. And I think it's pretty obvious it's pretty obvious here how our mean fails to capture central tendency, right? So here's our mean, 137, 833. That's, that's here somewhere. And that's more than all of these other people are making, right? And so if we are looking for something that's a little more central, it's probably going to be this 89,500. And, there's still something, well, that seems more reasonable, right? Something in here does seem more reasonable. It would probably be better for us to get a lot more samples, right? Like, obviously, the more samples you have, the better. So, we'd probably want to get just a bunch more to really fill this in. But we can see that one of these is more representative than the other, and it's likely, well, it's pretty clear that this is an outlier, right? We call these outliers. It's not clear offhand if 24,000 is an outlier. We'd have to make a decision about that, but offhand it does look like it might be. It might be right on the edge of being an outlier by some, conventional standpoint. And we'll kind of look at that. So the takeaway here is that the median is resistant to outliers, and there are certain types of data that are prone to having outliers, definitely, especially things like housing prices and income. Those tend to have outliers. The price of related goods, right? You might have, like if we're talking fingernail clippers or something, most fingernail clippers are going to cost around the same amount. We might have some dollar store ones. We might have some other, qualities of ones. And then somebody out there has like a $300 pair of fingernail clippers. And there's very little in between, like some decent ones, which are probably, I don't know, maybe $10 or $12 or something, and somebody's 300 pair of fingernail clippers. And this is just the nature of luxury goods, right? So, actually, here's an example, right, where we're considering mean and median directly in terms of income, right? Income is one of those classic examples. Car prices, right? Car prices is a really good example of this as well. We're going to have a few cars that far exceed cost, and would pull the mean to the right in a way that isn't going to give us a good measure of central tendency. So there's a couple generalized statements here that we can consider. So median is preferable when we have outliers, but also we want to have enough data that it has a fairly standard spread, right? if we have really fiercely bimodal data, median might not be very helpful, and it might be better to split our data set into two data sets. Mean is preferable for large data sets with few outliers. That's generally going to be true, unless we have some extreme outliers, which could apply in the case of the mass of stars. What if we have some sample of stars and most of the stars are somewhere around the mass of our sun, and then we've got some star in there that's just massive, right? Some like superstar kind of thing that's out in the universe that just drags our average to the right. So few outliers, sure. Large data set with few outliers, but it's also dependent on the extreme of those outliers. And mode is preferable, obviously, with categorical data. Mode can be really helpful for things like sales data, where you may be asking a different kind of question, like what item are we selling the most? And even if you're looking at the sale prices and that's your data set, well, if you're getting a lot of $4 sales, and that cacti are they sell for $4, then that is a helpful thing. And there's a kind of different sense of central tendency because that is such a highly sold item. Okay, cool. So let's consider the 5-number summary. This is a classical stats concept, and it's one of those things that you may or may not use in your everyday. But this is definitely a thing that people use, and let's just write a 5-number summary. We're going to keep this median function because we'll use it in the 5-number summary. And let's just consider what's in this, right? So in the 5-number summary, we have the min, we have the first quartile, Q1, we have the median, we have the third quartile, and we have the max. So we're going to just grab these, and I'll just grab all of that. Just so it's up here, and we'll just code this bit by bit. Oh, whoops. Let me just pull this over. All right. So call this 5-number summary, and we're going to pass in some list, right? And the min, well, we have a method that gets the min, right? So min is going to get the min of the list. Max is going to get the max of the list. And notice what I'm doing here. I'm just doing min underscore because min is actually a reserved word. I could name this something like min list or something like that, but this is my tendency. I'll tend to do that. And then we can also get the median, which is going to be the median of the list. And let me make sure, yep, it's called median. And now we want to get our Q1, right, which is our 25th percentile. And this is just going to be the median of let's think about the best way to do this. It's going to be the median of the initial value to the up until the median value. Does that make sense? So we can go from so our Q1 is going to be the median from the sorted list, which we need to make. So let's say the sorted list is going to get the sorted version of the list. So this is going to be the median of the sorted list from the 0th index to the length of the list divided by 2 minus 1. Okay. Is that going to work? Oh, you know what? That is not going to work. Let me think about this for a second. What is the best way to get this? I think we want to just get the index of the median. Or the index closest to the median. So, Or we could just get the median. Let's just do this. Let's get the median of the sorted list from 0 to the length of the list over 2. And I think minus 1. Yeah, that looks good to me. Okay, so, and then Q2 is going to be the median of the sorted list from here until the end. Okay. Let's try that. I might need to adjust that just a little bit, but I believe that's correct. And notice I can leave this empty to just say, okay, this goes to the end. Okay. And then that's all we need, right? Q1, Q2, min, max, median, right? So I can return the min, the Q1, the median, Q3, and the max. So let's just make sure that this is working as we'd expect it to work. I'm going to copy in some data from, let's copy in data from our lesson. And then we can compare the results and fix this if we need to. So the 5-number summary on B, oh, whoops. That should say Q3. Okay. So let's see if this matches what we're seeing in here. Okay, so min is 1, and our max is 56. We got those. Median is 19. Here it's showing up as 19.0, which is fine. And oh, our median for B low should be 7, and we're showing 6.5. And the upper median should be 48. So let me see, is it just that? There we go. Okay. Yeah, so 1, 7, 19, 48, 56. Yeah, that's what I thought. Oh, right, because this is not inclusive anyway. So that's fine. Okay. So this is giving us the median of, this is giving us the 5-number summary for this list. So what do we do here? We got the min, right? We got the max, we got the median, and then we got the median from the lower half, which is what we're doing here. We got the median from the upper half, which is what we're doing here. So we could break this out if we wanted to, if we want to just show what this is. So let's call this, here we're calling it B low. Let's just call it list low. And let's print that. And then let's also get list high. And we'll print that as well. So I'll just print them here. So list low, and I'll just print list. Actually, since we're all using f strings all the time, let me go ahead and use an f string. So this will be list low, and this is that, and then list high, and it is that. Okay. So let's see how that goes. So 1, 4, 6, 7, 10, 14, 16, right? Is that, oh, 1, 4, 6, 7, 10, 14, 16, and then 22, 24 through 56. So that is working. Let's try this other data set and make sure we don't have to make any adjustments. You know, this is just sort of ad hoc testing. I probably could write some tests if I wanted to make this a little bit better, but you know, I'm just testing it out against the problems we have up here. So let's see if we get the same results. Okay, so here we get the low subset. Ooh. 1, 2, 5, 6, 7. Okay, no, that's right. And then we're including, in this case, 9, which we should exclude. So that's interesting. 1, 5, 9. We should have 18 over here. I see what's going on. In this case, we should exclude the median. And because of that, I need to adjust this somewhat, right? So in this case, we should adjust Q3 if we should adjust this in Q3 to be +1. So I'm just going to put in a little clause that says if the length of the list, yeah, let's say if the length of the list modulo 2 is 1, right? So if it's an odd length list, then move mid index by, let's move it by 1. Sorry, we'll do it by 1. Otherwise, we will do it by 0. So let's see if this works. For what we're trying to do here. Okay, so that works for that one. Let's try it for B and make sure that this is doing what we expect it to do for B as well. One, 7, 19, 48, 56. Okay, so yeah, this is one of those things where you kind of have to reason some of this out a little bit more than you'd expect to, and that's just because of the evenness or oddness of the length of your list. In this case, I just needed to start my my median at the correct place for an odd length list. So I'm going to snag this and set it aside, because I always sort of mess this up in real time when I'm writing this function. And if we look at the code snippets here, these are no less complex. This uses NumPy, and you're definitely welcome to start using NumPy. You know, NumPy has a lot of built-in summary stats materials. And, oh, interesting. Oh, yeah, all right. And NumPy also has a percentile function that you can just import. So, you know, and this warning is saying that this example is going to return a slightly different set of values for the 5-number summary because of how it partitions the data. And that's kind of what we ran into here. So I learned to partition the 5-number summary on odd length data with inclusion of the middle value, right? So the low value up and to including the middle value, and then the middle value up, including the middle value in the upper portion as well up until the end. And that's a less traditional way to do it. That's actually how I learned to do it, and that's not what I'm doing here. In this case, I'm excluding the middle value. So I assume there's an argument, a raging argument that's been happening for the last 60 years in statistics about this, or not at all, because everyone kind of does their own thing a little bit. But at the end of the day, I do think this is more conventional, not including the middle value in the 5-number summary. So yeah, that's right. I was going to snag this, and there we go. Just going to set this aside somewhere, and okay, cool. All right, so that's 5-number summary. Let's see what we have. We don't have that much time for variance and standard deviation.